Hello ladies, we're going to go through the final section, for now anyway, of chapter 3, and that's the graphs of exponentials. So you've looked at graphs before, linear graphs mostly. Exponential graphs, as you can see on the screen, things increase dramatically quickly or decrease. So if we've got growth, it's increasing quickly, and if it's decay, it decreases. So I'm just going to go through some of the dot points just to explain some things that you may have never heard of before, especially like an asymptote. So the first one, y equals 2x, y equals 0.4x, y equals 3 times 1.1x. They're all examples of exponential equations. So if your unknown or your x variable is a power, it's an exponential equation or relation. An asymptote is a line that a curve approaches by getting closer and closer to it, but never reaching. Okay, so you can see here your asymptote for this graph here, y equals 2x, is 0. So this exponential curve will keep going. Okay, so it'll keep going and it'll get the values of y will get smaller and smaller and smaller, but it will never cross the line y equals 0. So that's what an asymptote is. When you go on to do methods, you'll come across asymptotes a lot, because a lot of graphs that you deal with will have an asymptote. So the graph kind of skims it, but doesn't ever touch it, and it doesn't ever cross it. So you need to remember that. All right, a simple exponential rule is of the form y equals a to the power of x, where a is greater than 0 and a is not equal to 1. So if a was equal to 1, it would just be y is equal to a, yeah, because a to the power of 1 is just a. So the y-intercept is 1. Okay, and remember that's only when it's in the form y equals ax. Your graph can move up and down, which would make your y-intercept change. Y equals 0 is the equation of the asymptote. So same thing if you had a constant. So remember your equation of a line is y equals mx plus c. So c is your y-intercept, and that just basically is moving your line up or down. The same applies here, but we're just looking at an exponential in the form y equals a to the power of x. We're not looking at any transformations up and down. Okay, just looking at basic exponentials, simple in this case. The graph of y equals negative a to the power of x is the reflection of the graph, so that just means it's negative. So you can see here the green line. So it's just flipped on the x-axis. And the graph of a to the power of negative x is a reflection of y equals ax on the y-axis. So you can just see here our original one, the red line, y equals 2x. When we've got a negative power, it's just switched in the other direction. And then we've also got the green line. Okay, so those are the ones we're going to be looking at. Okay, but there's a whole range of exponential equations. All right, so I'm going to skip that last point. Let's keep moving on and 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 on. Okay, let's do some questions. All right, and you can also graph these on your calculator just like you would any other equation, and you can also solve. Okay, I didn't show you in the previous one how to solve, but same thing, solve, plug in your equation, comma x, spits out your answer. All right, sketch the graph of the following on the same set of axes, labeling the y-intercept and the point where x equals 1. Sorry. Okay. So remember, for all these graphs, we're going to have a asymptote on the x-axis at y equals 0, and they all have a y-intercept of 1. Okay, so the reason for, if you're wondering why is it 1? When you think our y-intercept is when x equals 0, and then any number, so let's say 2 to the power of 0 is 1, 6 to the power of 0 is also 1, 5 to the power of 0 is also 1, negative 100 to the power of 0 is 1. So remember your index laws, anything to the power of 0 is 1. So that's why it is the case. So let's look at question 1a. So we've got y equals 2x. We know the y-intercept is going to be 1. And it also says another point where x equals 1. So if we're graphing exponential equations, it's not necessarily the same as linear equations where you just need 2 points and you're drawing a straight line through those points. You've got to kind of think of, well, what other features of this graph are there? There's the asymptote. So for the ones that we're doing, it's only going to be the x-axis. So I might just draw our axes now, and because I'm doing this on the computer, it's not always the best. Okay, so remember we're going through y equals 1, and it said find another point where, or find the point where x equals 1. So 2 to the power of 1. So your other point is going to be 1, 2. So when x is equal to 1, y is equal to 2. And you can, if you want, do more points, but your values are going to get bigger very quickly. So if we let x equal, say 2, so 2 squared, we've got 4. So we've got 2, and we're going up to 4. So we're going to have, going through there, then your next point there is at 1, 2, and then your next point is up here. And if I kept going, you know, the next point would be 2 to the power of 3, which is 8. So it's going to curve. Now let's try to go as close to that line as, oh, this is good so far. See how it's curving? So try to curve it, and it goes up like that, and it will keep going. So I'm just going to put a little arrow. Now, if we were to do another line, which we are, come on, go away. Y equals 6x. Okay, again, it goes through this point here at 1. But this time when x equals 1, y is equal to, oh gosh, why did I do that again? 6 to the power of x. 6 to the power of 1, which is just 6. So this time we're going to have our next point is at 1, 6. So your line, same as the blue one, it's going to be a lot steeper. Okay, so that means the growth is a lot steeper. Okay, so you want, well, sorry, you don't want, that's just how it is. I was going to mention the coronavirus again, but I don't want to do that. Okay, let's move on. So question 2 is quite similar. Let's go off the phone. Okay, I think we're just comparing there. Question 3 was kind of done in the theory. So let's scroll on and maybe do question 4. Okay. It's pretty much the same thing. We're just dealing with different graphs. So let's have a look at question 5. Go back to blue. Okay, so question 5a, this time we've got y equals 2 to the negative x. So what we're doing is finding or labeling the y-intercept, finding the point where x equals 1. Okay, so remember your y-intercept is when x equals 0. So this is still going to be 2 to the power of 0 is at 1. Oops, I think I should have done my line this way. Okay, and then when x equals 1, we've got y equals 2 to the power of negative 1, which we know is a half. So when x is 1, y is going to be equal to a half. So we're going to down there. Now you're probably thinking, oh, what's that going to look like? This is why I always think it's good to get another point. So if I did say, let's let x equal maybe negative 2, I'm going to be left with y equals 2 to the power of negative 2, which is just y to the y equals 2 to the power of 2, which is 4. So when x equals -2, I got y equals, so that was 1. Well, my scale isn't the best, but you're up there. Okay, so you can join the dots and we're going in that direction. Okay, so same method. Okay, if you take your time, but if you just know what the family of exponential equations looks like, you would know when you've got a negative power, it looks like this, so it's reflected along the y-axis. But if it was a negative base, then it's reflected on the x-axis. Okay, I might leave it there because I don't want to make the video too long, but just take your time. You can graph these on your calculator if you need to. Just when you graph them, just make sure you know what the y-intercept is. So it's going to be 1 unless you have a negative base. And what was the other thing? Oh, and find another point. So usually x equals 1, but I always like to find another point as well, so you think that it's just a straight line, that you can actually draw a curve. And make sure you don't go over the line because your axis is your asymptote. Okay, bye-bye.